Yes, I'll talk about WarpX, which is a particle and cell code that can simulate different types of fusion concepts. And my name is Remi Lehe. I'm a scientist at Lawrence Berkeley National Lab, and I'm speaking on behalf of the whole WarpX team. So in that presentation, there's essentially two parts. I'll first give an overview of the particle and cell code WarpX and show some of the features that are available. And then I'll talk about some of the applications for fusion. So there's different types of fusion devices or different types of fusion concepts that are being modeled with WarpX. So just to place WarpX in context, so the different types of codes that are used in fusion. So I'll place WarpX in that landscape. So first of all, WarpX is a code to simulate plasma evolution. So in this session we heard about codes that compute the equilibrium, so sort of time-independent equilibrium. But WarpX is different. It calculates the evolution in time of the plasma. So as physicists, we know that the evolution of time of the plasma is governed by the Vlasov-Maxwell system. So the Vlasov equation, where there are the E and B fields, and the E and B fields are given by the Maxwell equations or approximations of the Maxwell equations. So there's several ways to solve the system to compute the evolution of the plasma. One is fluid codes that compute moments of f of the distribution function. So for instance, the density, the velocity on a spatial grid, but they require closure assumptions which may not capture kinetic effects. So to capture kinetic effects, you need either a Vlasov-Fokker-Planck code or particle and cell code. So Vlasov-Fokker-Planck codes represent the function f on the grid in space and velocity. But that can be very expensive because if you use 3D in space and 3D in geometry, it's a 60 problem. So the 60 grid can be very expensive. So finally, particle and cell codes represent f with discrete particles moving through a spatial grid. And so WarpX is a particle and cell code. So moreover, WarpX is a generic particle and cell code. So what do I mean by that? So for tokamaks and accelerator, I think people often use specialized particle and cell codes. So that means that those codes make strong assumptions. So the gyrokinetic approximation, for instance, which applies very well in tokamaks and accelerators. And usually the geometry of the grid follows the field lines. However, WarpX is not that kind of specialized code. So it's more generic, like it doesn't make the gyrokinetic approximation, for instance. It uses generic grid geometries. For that reason, it's more beneficial for other schemes than tokamaks and accelerators. So for instance, inertial fusion, as well as quote-unquote alternative schemes. So these are the various schemes that are proposed by private companies in particular these days. So again, sort of giving an overview of WarpX. As I said, WarpX is a particle and cell code. It's open source. You can find it on GitHub at this URL. It was created under the Exascale Computing Program, which was a program in the US to get codes ready to run on large-scale computing architectures. And it's now primarily funded through SIDAC, which again is a program in the US. It has many applications, so not only fusion. It was developed originally for laser plasma acceleration. It's been used for astrophysical plasma spacecraft interactions. But then today I'll talk about the applications to fusion plasma. So because of the fact that it was created under the Exascale program, it specifically targets high performance computing. And it was really aimed to be able to run on those large scale computers. So it's portable across computing architectures. WarpX is written in C++, but the code can be compiled for CPUs, GPUs, and NVIDIA GPUs, AMD GPUs. So we don't have separate source code for these different architectures, and instead it's just at compile time that you select the architecture. It's massively parallel. It scales across thousands of CPUs and GPU nodes. In particular, in 2022, WarpX was recognized by the Gordon Bell Prize, which is a famous prize in HPC. And then it has general features that make it efficient, including dynamic load balancing and mesh refinement. We try to follow modern software development practices to make the code user-friendly and robust. That includes an online documentation. We also have an online tutorial that was presented today by Ariana Formenti, a member of the team, at 9:30. So if you missed it, you can still go to that URL and follow the tutorial. We have automated code at this point, more, like a few hundreds physics code that run with every code change or every PR in WarpX. And it's installable through various managers, including Conda if you want to run it on your laptop, but also SPAC for HPC platforms. It has a large developer community. A lot of the developers are at Berkeley Lab, either in the physics division, that's the first line here, or in the computational science division. But we have also other developers at Livermore National Lab, at CA in France, DAISY in Germany, as well as contributors from some of the private companies, so TA and Helion, also contribute to the development of the open source code. And then also Rochester, Kale Weishman is also contributing. In the next few slides, I'll go over some of the specific features of WarpX and that make it very flexible. So one feature is it has several field solvers, saying that the evolution of the plasma depends on the E and B field, and that the evolution of the E and B field is governed by the Maxwell equation, but you can make several approximations, and so use different field solvers for that. So we have a fully electromagnetic field solver that captures the full Maxwell equation, including the propagation of electromagnetic waves. But then we also have an approximate Ohm's law hybrid peak mode, where so that's a type of model that's often used in fusion plasma and neglects electromagnetic waves, treats the ions as kinetic, but the electrons as fluid. And then we also have electrostatic and magnetostatic modes. And we support several geometries for the mesh 1D, 2D, 3D Cartesian, as well as cylindrical geometry. We also support metallic boundaries with arbitrary shapes, and that's important for various fusion devices that have potential interaction between the plasma and the walls. So the metallic field boundaries, the metallic boundaries are taken into account by both the field solver, for instance, by setting an electrostatic potential on the boundary, and the particles, because particles are absorbed or reflected at the boundary. We also have several multi-physics modules, including Coulomb scattering, fusion reactions, charge exchange, impact ionization, elastic scattering, etc. Another feature that's interesting is even though WarpX is written in C++, sometimes you don't want all the codes that you need to be directly in C++. So one example is if some private companies are using WarpX and this specific multi-physics modules that are proprietary, then they may want to keep that outside of the C++ code. Another example is if you have pre-trained ML models, usually you wouldn't want to commit the whole ML model with the weights, etc., in the C++ code. And so for those use cases, users can maintain this type of code in a separate Python file that interfaces with WarpX. And so WarpX, the C++ code, provides an interface, a Python interface that has full access to all the data, the fields, and the particles. And so you can write very easily Python models that will interact very deeply with the structures in the code. All right, so in the second part of the code, I'll go over some of the applications of WarpX to fusion. The first one is inertial fusion. So in 2023, the WarpX team obtained SciDAC funding to look specifically at inertial fusion. So inertial fusion is very often modeled with fluid codes. And so the aim of that particular project is to use particle and cell code to capture the kinetic effects in inertial fusion that are not captured with the fluid codes. So it's a large team, again, with the scientists from Lawrence Livermore, Lawrence Berkeley Lab, Rochester, and also collaborators from Kitware. And again, the aim is to use the particle and cell code to look at different aspects of inertial fusion. So in inertial fusion, an incident laser impinges on the target and compresses it like this. And so there's different stages, different types of physics that happen as the laser propagates in the plasma that surrounds that target. There can be various instabilities. And so WarpX will be used to study those laser plasma instabilities, study laser absorption and transport of energy in the target, and then look at the hotspot physics. Another use case is WarpX is being used by TAE. So TAE was developing a certain number of codes, and some of those codes right now are being transitioned to WarpX. So they're working with us, and we're very grateful. And they're bringing some of those modules into WarpX, into the open source code. Some of that work has been published in that Physics of Plasma. So specifically regarding the Ohm's law hybrid field solver that I was talking about. But since then they've added also other features in WarpX, including binary collisions and macroparticle merging. Yet another company that's using WarpX is Avalanche. So their concept is a device that confines ions and electrons with a mix of electrostatic fields and magnetic fields. And again, we collaborated with them, and that led to many other features in WarpX. That's when we started this collaboration. That's when we added DT fusion in WarpX, and then other features such as loading fields from external files, mesh refinement in certain geometries, interaction between particles and the boundaries. The last example is WarpX is being used to simulate laser ion acceleration at the Bella Center. So the Bella Center is an experimental facility that is located at Berkeley Lab. It has a few high-power laser systems, and it's used routinely to accelerate particles with lasers. Some of those laser acceleration schemes have applications in fusion, in particular for fast ignition in inertial fusion. And so WarpX is used to model or to simulate the acceleration of particles by laser. So in conclusion, WarpX is an open source high performance speak code that's suitable for modeling various types of fusion concepts. Our activities in that sector are expanding. So as I said, originally WarpX was developed for laser plasma acceleration, but we have now more and more use cases for applications in fusion. Most developments are synergistic with the plasma acceleration, so that is still the core activity of the team. And we welcome any new collaboration with public and private sector, so feel free to reach out. And again, the code is on GitHub, so feel free to open new PRs or bring up issues. And with that, yeah, thank you. And if there's any question, please don't hesitate.
That was really nice again. Thank you, Remi. While people are thinking about their questions, putting them in the chat, I will take advantage of my position to ask a first question again. So I'm interested in how you manage an open source software project like this, where you've got lots of external users from quite sort of diverse areas. Mm-hmm. It seems like a lot of your features seem to be driven by external users and what they wanted. So like, how do you manage that versus like a roadmap of features that you want to implement? Is there any tension there, or do you let your use cases come from the community? How does that kind of work?
Yeah, it is to a large extent, I think, driven by use cases and by what the users request. So there's several ways to request new features. We have issues on GitHub. We have weekly meetings where also people sometimes bring up new features. And so oftentimes during those meetings, we look at what features users want and which one are most synergistic with what we want to do in general, or which features are requested by many users, and we sort of pick some of those. Some of the features that are implemented, of course, depend on funding, right? We have specific funding for specific fusion problems, so that also determines which one we implement. And oftentimes we get also contributions for free, quote unquote, so with other users that want features, but actually implement them themselves. And that's sort of the ideal case if it fits neatly in the code.
Yeah, absolutely. Cool. Thank you. We got a question from Nick, so asking how interoperable is WarpX with the OpenPMD metadata standard for particle mesh data, and I do see Axel in the audience as well that probably would have something to say on this too. But yeah.
Yeah, so Axel, who is the founder of the OpenPMD standard, is part of the WarpX team, and so we fully support OpenPMD in WarpX for output. So all the WarpX output for the fields and particle is in OpenPMD, as well as for input. So sometimes in input we take field maps that are to be applied to particles, and that's also read in OpenPMD format.
Yeah, so for those that are unfamiliar, OpenPMD is a standard, the PMD stands for particle mesh data, and for anybody that's interested, do follow the link that Nick's put in the Q&A there and check it out. Brilliant, just waiting to see if there are any other questions coming in. So we have about 1 minute left. Going once, going twice. No, all good. So I want to. I see a hand up there from somebody, but let me see, Jean-Luc. Let me just see if I can spotlight you so you can ask your question live. Let's have a look. Let's see. Yeah, there we go.
Yeah, no, okay. I just wanted to add to Remi's response about how we manage. We have weekly meetings where basically we attended also by all the users, and we can answer question, and then we have all these other channels to. So anyway, okay. Since there's only I think less than a minute left, that's all I'll say.
Brilliant. No, thank you for that. Cheers. And let me just see if there's just one very final one here asking, is there any features dealing with relativistic particles?
Yeah, absolutely. So again, because WarpX was initially developed for laser plasma acceleration, so that is acceleration of particles. In those use cases, the particles go very close to the speed of light, and so pretty much all of WarpX, with the exception of maybe a few multi-physics modules, all of WarpX is relativistic. So in particular, the particle pusher is relativistic.